Okay, I wanted to try something a little bit different for the sedimentation and solids loading rate questions here in Chapter 5. Rather than do example problems for you, I thought I'd create a little video to help you think through the problems. I guess let me know how this works out for you. But the first thing I wanted to talk about was in class the other night, we had a question about where does this pounds formula come from? And so, in thinking about it just a little bit, this I think is where it comes from. And in the interest of full disclosure, when I learned this formula and when I took this class, the instructor told me, don't worry about where it comes from, just know that it works. But as you can see, the pounds formula that we discussed looks like this: flow in million gallons times milligrams per liter times 8.34 will give you a number in pounds. And this is why. Milligrams per liter is equivalent to parts per million. So 120 milligrams per liter would be equal to 120 parts per million. And so that's why when you plug numbers into this formula, we need to convert flow into million gallons. Because when we do that and multiply it by parts per million, hopefully at this point you realize that 120 parts per million times 1 million gallons would mean that you would have the equivalent of 120 gallons. 120 parts per million times 1 million would give you 120 parts. And then at that point, since you have 120 gallons or 120 parts, if you multiply that 120 times 8.34 pounds in a gallon, that would give you the number in total pounds. So that's why the formula is set up the way it is, and that's also why we need to factor in specific gravity. So in some of these questions, if you were given a specific gravity different than 1, you would have to include that specific gravity to make the conversion from 8.34 pounds per gallon to a different number of pounds per gallon depending on the specific gravity. So that's where the pounds formula comes from. Almost all of the pounds formula questions that you're going to be doing from here on out are going to be with a substance that has a specific gravity of 1. So most of the time we can ignore the specific gravity. And if the specific gravity is not 1, you'll be given that in the information to solve the problem. So in looking at these problems in Chapter 5, as far as sedimentation and solids loading rate, you can use the pounds formula for problems 1, 2, 5, and 6. You have to calculate pounds. So problem number 1, how many pounds of BOD are removed from a primary clarifier? Be careful when you read that question. They're asking for pounds removed. So think about it this way. If 185 milligrams per liter go into the clarifier and 128 milligrams per liter come out, what was actually removed? And hopefully, if you think about it a little bit, you realize that the difference between 185 and 128 would be what was removed, and then you can plug that amount of milligrams per liter into your pounds formula. And then number 2 is just a straight pounds formula problem. Number 5, you have to calculate solids loading rate in pounds per day per square foot. Let me scroll down here. So pounds per day per square foot. again, like I mentioned in the previous videos, the problem is actually telling you how to set your equation up. You have to calculate pounds per day using the pounds formula, and then you also have to calculate the surface area of the clarifier in square feet. And then, as I continue to reinforce, anytime you see that word per, you know you have a division problem. And so at the very end of the equation, you're going to have pounds per day on top and square feet on the bottom. And do one more division problem to get pounds per day per square foot. And while we're talking about that sort of problem, you also have in problem number 6 a hydraulic loading rate question, which is going to be gallons per day per square foot. So again, calculate the gallons per day. That goes on top. And then the surface area in square feet goes on the bottom for one last division problem. And I'll give you a hint in this question. You need to add the two flow rates that were given to you together. We haven't really covered solids handling yet, but in a gravity thickener, it's not uncommon to pump not only sludge to the gravity thickener, but also a constant flow of treated effluent. And the reason we do that is to keep that gravity thickener from becoming anaerobic or septic. So a constant flow of fresh water helps keep that gravity thickener operating properly. So most of the time you're going to have two separate flows. The sludge that you want to thicken in it, and then what is called elutriation water, which is a big fancy word you don't need to remember. But you'll be pumping relatively fresh water to that gravity thickener all the time. That helps the sludge thicken and sink to the bottom, while also allowing that gravity thickener, which looks an awful lot like a clarifier, to have water constantly flowing out of the top. And that allows, at least in the case of our gravity thickener, for that rotating mechanism on the top to be in constant contact with the surface of the water and collect anything that might be floating on top. If you weren't constantly feeding water to that tank, then you'd get a buildup of floating sludge, grease, that sort of thing would be able to build up on top of the surface. So a couple questions here. I mean, one about a secondary clarifier, and then one about a gravity thickener that we haven't actually covered those concepts in class yet. So I just wanted to give you a hint. You need to add the flows together when doing those math problems. And then the last thing I'll touch on is the percent removal formula. This is one of those formulas that, to me, when you write it out, it looks more complicated than it is. In minus the out times the in times 100 looks a little bit more complicated than it really is. When we're talking about removal efficiency, we're talking about the percent removed. And then I wrote up a pretty simple example. I tried to use 100 and 25 so that you could kind of visualize this without having to actually do the math. Obviously, if you start with a 100 and you have 25 left over, that means you removed 75 or 75%. So when I plug those numbers into that formula, 100 minus 25, so basically what you started with minus what's left over is going to tell you how much was removed, and then you divide that by the number that you started with, and when you divide that out you get 0.75, and then this last part here times 100, you're just converting 0.75 into 75%. So if If you're pretty comfortable with converting decimals to percentages and you know that 0.75 equals 75%, you can kind of forget about that times 100 part of the formula. So that's why it's in there. And again, as I mentioned, just to me, when I look at that formula on paper, it looks, adding that times 100 in the parentheses just kind of makes it look a little bit more difficult than it really is when you apply it. So hopefully this video helps you with those sedimentation problems. The last couple pages on sludge pumping and thickening, I will do specific videos for those types of problems because I have to explain to you guys a little bit about where the numbers come from. But hopefully this video helps with the sedimentation and percent removal problems. If you guys have any problems with these specific math problems, just give me a text or call me or whatever, and I'll be happy to help you out and try to talk you through it.